Hey, I'm Ryan Nicol, CTO at DSA Ocean, and today we're going to talk about mixing and matching hydrodynamics in ProteusDS and when you'd want to do that. So for the purposes of this, I wanted to set up a simple example to make the comparison a little bit easier to illustrate and explain. I'm going to turn on the water surface in the visualizer here. So we have three models of this box barge system, and using this because we use this in a few of the other video tutorials. It's just a 20 meter by 20 meter by 2 meter high box. Now, in the first model that we've got here, we have a hydrodynamic database imported with the wave radiation and diffraction effects as calculated by Shipmo 3D toolset, but it's also got the linear incident wave loads in the database as well as a linear hydrostatic restoring stiffness. So this is all basically provided as part of the hydrodynamic database, and it's a great starting point. It does a lot. But I wanted to make a comparison because the other thing that you can do in ProteusDS simulation toolbox is you can make a cuboid and have the mass properties here set up exactly the same. Now the cuboid model does have some viscous drag and constant added mass, but based on the wetted volume of the structure, and like how does that make a difference to the motions when you don't have the wave radiation and diffraction effects? So that's the second model that we've got here. And then the third model is mixing and matching the hydrodynamic effects. So the only thing that we're using from the hydrodynamic database is the wave radiation and diffraction loads. And then we are using the cuboid mesh for the nonlinear calculation of the incident wave and buoyancy forces on the system. So there's two types. I've already done a simulation of these systems. There's two things I want to highlight. I started them all off above the water because I wanted to show the damping effect that the wave radiation has. The other part I wanted to highlight is that we have a slow ramp on of airy waves in here. It's a pretty aggressive wave period at 6 seconds and pretty steep with 2 meter wave height. Though it's pretty short and steep, it is definitely something that's possible in an extreme coastal environment where there's a lot of wind-driven storm conditions. So we'll check out the results in post-PDS, and again, I've already got them loaded and simulated here. The first thing I want to highlight, so they're all going to free fall into the water, and this middle barge in the system, you can see right away that there's quite a lot, it's a lot more active, and that's because there is no damping effect from the wave radiation forces. So, I mean, it's not a bad approximation just to get started really, really quickly, but certainly you do see a difference in the two other systems that have wave radiation effects. And even just looking down, you can see it's still kind of quite a bit more active in heave compared to these two. Now, that sort of leads to the next question. Well, why would you want to do nonlinear wave excitation and buoyancy? And the reason you would want to do that is in more extreme conditions or when the system is moving a lot, which may be near a resonant condition. And what's happening is you may be getting a lot of change in the wetted area of the hull. So you can kind of see this a little bit illustrated by just looking at the side here. And what is happening is from the motion of the system, you're getting these changes in the wetted area. And the hydrodynamics calculated by the Shipmo 3D toolset, they're all linearized about an assumed constant wetted hull area, including the wave excitation effects. So sometimes in extreme conditions, you can see the bow end or the stern end digging into a wave, and that can make some really big differences in the loads. So if you do want to mix and match the hydrodynamic loads, it's definitely something you have to be a little bit careful about double counting. And what I mean by that is, so we're using the wave radiation and diffraction effects. If we look at the feature definition for this, a rad diff only, you can see we have these flags on for diffraction loading and wave radiation only. And then if you look at the cuboid model, we've deliberately set all the added mass coefficients to 0 because otherwise that would be double counting with the added mass effects with the wave radiation calculations. We do leave on the drag coefficients because those are viscous in nature, and there is an additional damping effect from wave radiation as well, but it's linear and it's separate from these physics effects. And so, yeah, just an important note on that. Just be careful and to be aware that it is possible to have some detrimental overlap if you're not aware of that. So anyway, just a little note. I think it depends on your application about what's best of what you're doing. These are very squat box barges, so they don't have too much of a problem with lots of change in the wetted area, but certainly if you had a longer barge, which is certainly much more realistic, you may see quite a lot more changes in the wetted area. So something to keep an eye on. All right, thanks for watching.